Greetings, this is Professor Roman. Let's continue the lectures on linear algebra. As promised last time, we're now going to prove the famous Cayley-Hamilton theorem, which states that the minimal polynomial of a finite dimensional linear operator divides the characteristic polynomial. As is often the case, we prefer to work with matrices rather than operators. So let A be an n by n matrix over the base field. Theorem 7.24 tells us that the minimal polynomial and the characteristic polynomial of A have the same set of roots. In any field, actually, that contains the entries of the matrix, although they don't necessarily have the same multiset of roots. In other words, the multiplicities of the roots are not necessarily the same in the two polynomials. Theorem 740, which was the last theorem we did in the previous lecture, where we determined a lower bound for the dimensions of the kernels of the primary summands in the primary decomposition. This theorem is actually the key to the proof that the minimal polynomial divides the characteristic polynomial. This statement is often reworded, and you may find theorems in other books to this effect. A matrix satisfies its own characteristic polynomial. And that's equivalent to saying that since A satisfies this polynomial, it must be a multiple of the minimal polynomial of A. Since these two polynomials, the minimal and characteristic polynomial, are field independent, we can choose any base field that we want for the matrix. So we'll choose one that obviously the field must contain the entries of the matrix. So we'll choose one that contains the entries of the matrix and is algebraically closed. Now, there is a theorem in field theory that says every field is contained in an algebraically closed field. But this is neither the time nor the place to get into those details to prove that. We'd have to study field theory. So I'm going to have to ask you just to accept that fact. When I get to the field theory lectures, which will be sometime in the future, I will prove this result. On the other hand, if A is a rational, real, or complex matrix, then we can take the base field to be the complex field, which is algebraically closed. Although even that, the proof of that is not at all trivial and wouldn't belong in the course on linear algebra. So either way, you will have to take something on faith. But because we are choosing for our base field an algebraically closed field, the minimal polynomial of A splits into a product of linear factors. And all of the primary summands are linear summands. They look like this. Now, the minimal polynomial of A restricted to a primary summand is this power of a linear polynomial. It's this polynomial right here. We've proved that in the last lecture. And since the characteristic polynomial of this restriction of a to k sub I has the same root set as the minimal polynomial, it must also be some power of x minus lambda I. Both of these have the same base, x minus lambda I, but possibly different powers. The degree f sub I of the characteristic polynomial is equal to the dimension of k sub I as a vector space. So fi equals the dimension of k sub I, and by Theorem 740, which we proved last time, that is bigger than or equal to e sub I. So these two polynomials, the minimal polynomial and the characteristic polynomial of the matrix, have the same linear factors. They both factor into a product of linear factors. They have the same linear factors, but the multiplicities in the characteristic polynomial are bigger than or equal to the ones in the minimal polynomial. And so the characteristic polynomial is divisible by the minimal polynomial. We could line up the minimal polynomial right under here. These would be E1, EK, same roots, so same linear factors, but each of the f's is bigger than or equal to the e's, so the minimal polynomial divides the characteristic polynomial. This wasn't a very complicated proof of such a famous theorem, but the reason is because we had already proved theorem, what was it, Theorem 740, that this result here, that did take quite a bit of effort. Okay, so I've written the Cayley-Hamilton theorem in two versions, a matrix version and an operator version, but they're essentially identical. We don't need the matrix version since a matrix is an operator. But so it simply says that the minimal polynomial of an operator divides the characteristic polynomial, or that a linear operator satisfies its own characteristic polynomial. Incidentally, there's a very famous purported proof of this result. You would just take the characteristic polynomial, so this is CA of x, and just substitute for x, substitute a. You get determinant of a minus a, which is determinant of 0, and that's 0. This sort of purported proof shows up on exams sometimes, and the question is this a valid proof? And the answer is no. But in my experience, when I ask students in the classroom what's wrong, they generally don't know. So it's something worth thinking about. I left it as an exercise in my book. I don't remember whether I included a solution to this one in the back of the book or not, but it's something you should be aware of so you don't get trapped by this. It's something you should think about until you can convince yourself that there's something wrong with that proof. It looks rather convincing. Let's take a look at some of the uses of the Cayley-Hamilton theorem. We discovered earlier in this chapter that every matrix or every operator finite dimensional operator, satisfies some non-trivial polynomial. And the way we did it was for matrices, the dimension of this vector space is n squared, the n by n matrices. This list of polynomials must therefore be linearly dependent, because there's n squared plus 1 of them. And a linear dependency here amounts to a polynomial of degree at most n squared that is satisfied by A. Well, the Cayley-Hamilton theorem improves quite a bit on this by telling us that there's a polynomial of degree n, not n squared, but n, that is satisfied by A. In fact, it tells us it's the characteristic polynomial. So that in itself is an improvement. And here is how we can use the Cayley-Hamilton theorem in a variety of ways. Just calculation with a matrix. Take this matrix, for example, and suppose I asked you to compute P of A, where P of X is this simple polynomial. This would be a good test question also. Well, if you started to just substitute into this polynomial, you'd go crazy pretty soon. Even trying to compute the 13th power would be ridiculous. But you can factor, you can divide the characteristic polynomial, which is relatively easy to compute, into this polynomial. P of X will be, this is the quotient, the divisor, and the remainder. Now P of A is equal to a to the 10th plus 3a minus 1 times CA of A plus A plus 1, but CA of A is 0. So P of A is just A plus 1. You just add the identity to A. So that's a huge savings in labor. Another example of where the Cayley-Hamilton theorem can come in handy is computing the inverse of a matrix. I'm not suggesting this is the most efficient way. Gaussian elimination tends to be, but at least this is interesting. Here's a small matrix we might want the inverse of. So this is the characteristic polynomial, and so the Cayley-Hamilton theorem gives us this, and a little algebra tells us this. And so A inverse is in fact 1/2 the quantity A minus 5. And that's easy to compute. The Cayley-Hamilton theorem tells us that the minimal polynomial divides the characteristic polynomial. It's a factor of the characteristic polynomial, and it has to have the same root set. And that can be a huge help in finding the minimal polynomial of a matrix, which in general could be difficult. I mean, it can still be difficult even using the following technique, but at least it works in some cases. Here's a 3×3 matrix. The characteristic polynomial is this polynomial, which we factor. Quantity x minus 1 squared times quantity x minus 2. So the Cayley-Hamilton theorem tells us that the minimal polynomial must be one of these two. It has to have the same roots, so it has to have at least x minus 1 to the first power and at least x minus 1 to the second power, but since it divides this polynomial, these are the only two choices. And routine calculation shows us that P of A is in fact 0. And so that is the minimal polynomial. Finally, let's do a more or less complete analysis of a matrix using, in part at least, the Cayley-Hamilton theorem. Here's the 3 by 3 matrix. We can compute the characteristic polynomial by the usual methods. The minimal polynomial is therefore one of these two. Again, we plug in to the, starting with the polynomial of smallest degree, and that's P of x. So P of A is not 0, so this must be the minimal polynomial. So actually, in this case, the minimal polynomial is the same as the characteristic polynomial. The eigenspaces, we can compute the spectrum of the matrix is the set 1, 2. The roots of either polynomial, in this case they're the same. The algebraic multiplicities are given here. They're found from the characteristic polynomial. The eigenspaces are kernels, and one can compute that by solving a system of linear equations. And from here we get the geometric multiplicities. They're both 1. So the eigenvalue 1 has the same algebraic multiplicity as geometric multiplicity. It's non-defective. The eigenvalue 2 is defective. This is the primary decomposition. It's in the summands, the primary summands are these two kernels. These are the minimal. They come from the factorization of the minimal polynomial, which again is the same as the characteristic polynomial. So it's right here. The kernel K1 is the eigenspace that we already actually computed. So, yeah, here it is. Same thing as we had before. The other primary summand is a generalized eigenspace. And so we would multiply this out, get a matrix, and find the kernel that way, and we'll get a basis for the kernel, these two vectors. As to matrix representation, a simple matrix representation for this matrix, we could use this order basis, V1, U1, U2. This is a basis, this by itself forms a basis for K1, and these two form a basis for K2. But a better choice in terms of getting the simplest possible matrix representation would be to use as many eigenvectors as possible. The eigenspace corresponding to lambda equals 2 is this kernel, which is contained in this kernel, which is the second primary summand. So we can get a different basis for K2 that includes the eigenvector that we computed a minute ago, V2. Oops, this doesn't belong there. All we have to note is that U1, this one, together with the eigenvector that we got before, let me go back here, this guy, V2, those two form a linearly independent set, and so they're a basis for K2. So now we take V1, which is all by itself a basis for K1, and these two together, V2 and U1, form a basis for K2. So this whole thing is a basis for F3, the whole space. And two of these are eigenvectors, which is nice. And so AV1 is V1, AV2 is 2V2. All we have to worry about is AU1, which we compute. And so the matrix representation for A looks like this. It's upper triangular and almost diagonal, not quite. This matrix is therefore similar to the original matrix. If we want the similarity matrix that will bring A to this form, we can use the change of basis, change of matrix representation formula. The representation of A with respect to this basis we just constructed, and here's the matrix of A with respect to the standard basis. This is the formula that connects those two. The matrix of A with respect to the standard matrix, of course, is A itself, so that's why this is A right here. And the change of basis matrix from B to S3, we take the three basis vectors from B, we take their coordinates with respect to the standard basis vector, the standard basis. And so we get this matrix. So that goes here, and its inverse goes here. And this is the formula, the similarity relation that sends A to this nice looking matrix. Okay. So that's more or less a complete analysis of this matrix.